Okay, second property due to intermolecular forces is a property known as cohesion. Right? So cohesion is something that we talked about or was on your warm-up. And then some of you brought that word up in talking with the lab. Cohesion is the official scientific term of sticking together, pretty much. Have any of you guys seen, or maybe you have them at your houses? So some houses nowadays have like their gutter, right, that the rain falls in. But then instead of having like a pipe that goes to the dirt or the ground, they just have a big, thick chain. Shake your head if you've if I've seen that, if you have. Some people know what I'm talking about? Anyone have that on their house? Okay, well, it's a thing. Look around. You'll see it every once in a while. But the way that it works is through cohesion and adhesion. Okay? The water goes in the drain, and if it wasn't for cohesion and adhesion, then it would just waterfall off your house. But the chain, the water sticks to it and just goes down to the ground. I don't think there's a point to it besides maybe it looks cooler than pipe, but maybe there's a point. But it works the same way because the water molecules stick together. So, just like boiling point, things with strong intermolecular forces have strong cohesive forces as well. Once again, going back to the idea of our little magnets. Okay? Another word, and we've already used this before, but let's link it to IMFs, is surface tension. Okay? This is probably my favorite visualization when I think of surface tension. Okay? Like we talked about with belly flopping into a swimming pool, the little water molecules are magnets, and they're playing Red Rover against you. And so it creates this tension across the surface, and particularly if it's a small amount, that's why you get little beads of water, is because all the water is holding on to each other, and that creates a circle. If they weren't really holding on to each other, then it would just be more flat. Okay? So, once again, the higher the surface tension, say ST surface tension means higher IMFs. So I've always wanted to try this. I don't have the means to do so. So if one of you do, let us know and we can test it. I've always been curious to try, because water has high surface tension, right? So that's why belly flopping hurts. What if we tried belly flopping into a pool filled with oil? Because oil has really low forces. Like, yeah. I don't know for sure because the science makes sense, but I want to see it.
Wouldn't you also sink down really fast too?
Well, so that's the other problem is because the surface tension of water helps you swim in water. So can you swim in oil? I don't know.
No, it'd be fine if it
I think it could be shallow, but belly flopping into something shallow doesn't sound safe. Oh my gosh, can you imagine getting that off of you? That would be very problematic. But if any of you want to donate, just 100 gallons of oil in the swimming pool, and then volunteer yourself, we can test this. So, always been curious to try. If Mythbusters were still a thing, I'd send it into them, but they're not around anymore.
You can send it to Perfect.
Do they do weird? I thought they just do tricks and stuff, or do they do weird things? Yeah.
Mr. Beast did it.
Someone mentioned him last period too. They're like, he'd probably do it. So. Okay, but that's surface tension, and it's linked to IMFs. Okay. Another property we get is this thing known as capillary action. Okay. So next time if you still believe in straws, okay, next time you have a cup of water, it has to be a clear straw, and a clear straw inside of it, you can observe capillary action. A straw inside a cup of water will have higher level of liquid in the straw than where the water actually is. This is what it would look like in your glass of water at the restaurant. The reason why the water goes up the tube is because of intermolecular forces. The little water molecules can magnetize to each other and climb up. Now, any guess of what prevents them from just climbing up and out of the straw? Gravity, right? gravity pushes down, and so they can only climb so high. The bigger the straw, the harder it is for them to climb. So if you had a wider straw, you wouldn't see it climb as high. Now, this is exactly how there's things in hospitals and doctors' offices called capillary tubes. Has anyone ever seen one of those before? Can you describe, Jeff, like, do you remember what it looked like?
Isn't it kind of like there's like a little bag of water that they have hanging on like a weird rack thingy, and then that has like this really small white tube?
Oh, you're mixing up with something else,
Oh, okay.
but not a bad thought.
Don't they have like little V-shaped valves that so like to prevent backflow, so like it's like little layers?
Oh, that's something else, but that also works for intermolecular forces as well. A capillary tube is literally just a very, very, very thin glass tube, like smaller than a coffee straw, like teeny tiny. And they use these often just to gather very small samples of something. So if you take a capillary tube, because it's so small, like often they'll do it like if they prick your finger and they're going to just take that small amount of blood, okay? Sorry if blood grosses anybody out. So if you prick your finger and then they stick the capillary tube to it, it almost looks like magic because it looks like the blood just goes up the straw, like it sucks it up. So maybe you have seen, you just didn't know what it's called, okay? It's not sucking it up the straw, it's just so small that the molecules can climb on top of each other and the walls and go up without any suction needed. Because once again, it's such a small tube. I'll have to see, sometimes the biology department has some and we can, it's cool because you, like if there's a little puddle on your desk, you can just like touch the straw to the puddle and it looks like it just like sucks it up for you. Yeah, Jeff?
So with the surface tension, how come it's only on the surface, like really? How come like when you get past the surface, things can sink?
So the biggest part of it, if you kind of think of like, so here's our surface, right? Is because at the surface, the molecules are not being held in all directions, right? They're being held like, how do I put it? So here's like our little waters, right? So water we can draw like as a little Mickey Mouse guy because it's a bent shape, okay? And so they're like being held in this with the different hydrogen bonds and things. And so that's why it creates more of a tension at the surface. It's because they're being held just downward.
Not being distributed.
And so it's, but rather than like in 360 degrees it all happening, it's only happening there. Does that make sense? And so then once you break it, once the hydrogen bonds start to break, it's also kind of a domino effect of this one breaks and then that one breaks. And so then it breaks it as you keep going through it. Does that make sense? But it's also why, that's why you can still swim through water, is because those forces still do exist. Just because you're under the water doesn't mean the hydrogen bonds are gone, right? But that's why there's greater tension at the surface, is because it's only being pulled from in one direction, I guess you could say. Does that make sense? So, good question. Okay, next thing is solubility or dissolving. Okay? So I want you to think back to our lab, to I think it was station 6, okay? Where we had the oil and the water in the test tube together. Now, a lot of you on the papers claim that oil is less dense than water. And that's why that happened. It is a true fact, oil is less dense than water. But density doesn't prevent things from mixing. There's something else going on here. Yeah?
So with oil, it's a lipid, and like the structure of it, part of it is hydrophobic, so it hates water, wants to stay away.
So I'm going to take her biology terms and turn them to chemistry terms, because that's what you learn in biology. If you've taken biology class, you'll learn about, that fats and things are lipids and hydrophobic means water fearing, so it doesn't mix with water. A common misconception, though, is people will say that oil and water repel each other. What does it mean, like, scientifically, to repel? Push away. Oil and water are not pushing away from each other. Water's just so attracted to itself, it doesn't mix with the oil because it has such high intermolecular forces. So it's not that they're repelling, it's just water's more attracted to itself than it is to the oil, so they don't mix. So one of the things we look at with solubility and dissolving is similar typed forces. things that have strong forces can mix with things that also have strong forces. If something has weak forces and something else has strong forces, they're not going to mix because the one with strong forces will just stay together. Okay? So what I want to do for a second here is I want you to turn to your table buddy and have a quick discussion. Okay? Using now the term of intermolecular forces, discuss with your table buddy why then did we observe what we did with the food coloring. So we had the oil and the water and then we dropped the food coloring in. So explain that phenomenon based off intermolecular forces. Ready, set, go. Turn your table buddy and jump. Using the term intermolecular forces, explain how that works. How that works. This isn't a test right now. You're not going to be marked wrong or right, but there's a benefit to talking through out loud or not. Kinda. But density has nothing to do with molecular sound. Density just. So if something were purely just separated by density, you were to shake it up, they would mix somewhat. Does that make sense, the difference, Tyler? So good point to bring up though. Okay. Anyone willing to share their thought? Now, that question I just gave you is an example of a type of question you could see for 8.5 on the quiz, where I give you a phenomenon of some sort and you have to explain it based off intermolecular forces. Okay? All right. Anyone willing to share? Kent? Go for it.
So the food coloring can't has a strong force, and so it stays together while it's in oil.
Good. Pause there for a second. So visualize what she's saying, right? So the food coloring, you dropped it in, and what did it do through the oil? And it stayed in a little ball. That's because it has, the only reason it would do that is because it has very strong forces that holds it together. So it just falls through the oil as a little droplet. Okay, continue on.
And then once it reaches the water, it breaks because they both have a strong force.
Yeah. Its forces and water's forces are so similar that the magnets can then mix with each other. Now what I should get is there's food coloring that has opposite properties. Meaning it would have separated in the oil, but not in the water. Because in food coloring, there's certain things like candies that you, like chocolate. If you ever need to dye chocolate, normal food coloring won't work. You have to buy candy food coloring. Because it doesn't dissolve, because the chocolates have fats and things in them, and so it won't color it otherwise. Okay, so the takeaway here is a phrase that we use in chemistry called like dissolves like. Okay, what this means is that polar things can dissolve other polar things, because polar forces are the strong forces. If one substance is polar and one substance is non-polar, then they're not going to mix, because the polars hold too strong together. So we kind of, once again, we have this little catchphrase of like dissolves like. Polar can dissolve polar, non-polar can dissolve non-polar. Another connection to you, that's why inside of your body, so there's two different types of vitamins. There's water-soluble vitamins and there's fat-soluble vitamins. What that means is the water-soluble ones can dissolve in water. The fat ones only dissolve in fats. So one common misconception often with nutrition is sometimes there's a big thing of people like, oh, fats are bad. No, actually, if you didn't have any fats, your body could not use those fat-soluble vitamins because it would have nothing to dissolve them in. So fats are good, and you get the good types of fats because your body needs both kinds. So if you understand that comic, that's a good sign you understand what I'm trying to say here. If you don't understand it, then we need to keep talking. So look at the polar bears comic. Read what it says. If you're like, haha, I get it, then that's a good sign. If you don't get it, turn to your neighbor and ask them to explain it. Okay, what's the key thing we need to understand here to understand this comic? That water is polar, right? Water is a polar substance, and he is a polar bear, right? Like dissolves like. Okay? Okay, let's take a look at the example problem at the bottom. And then we'll get to our review. All right, so this is giving us 3 structures, and this is also similar to something you might see on the quiz for 8.5. I'm giving you 3 structures. So it gives you this one, this one, and this one. Okay? First question below says to list these substances in order from lowest to highest in boiling point. So what was the connection we just made between boiling point and molecules? So the higher the IMFs, the higher the boiling point. So a question that asks about boiling point is really asking you about its intermolecular forces. So let's review and go through these and identify what forces each of these substances have. Okay, so here's our review from last time. So first type of force is a London dispersion force. What types of molecules have those?
All of them.
Very good. So this one has London, this one has London, this one has London. Everything has London. All right, second type of force is dipole-dipole. How do I know if a molecule has that force? Good. So the question really is this molecule polar? Nope. So I'm going to make a note here so it's not polar. So it doesn't have dipole forces. Is this molecule polar? How do I know? Yeah, because one side is different from the other. So polar things are not symmetrical. So since it's polar, it has dipole forces. Okay? This one, shake your head yes or no. Is it polar? Yep, very good. That OH right on the side. So it has dipole forces because it is polar. All right, and then our last type of force was hydrogen bonding. What are the requirements to have hydrogen bonding? Good. H bonded to NO or F. So H, but no NO or F, so no hydrogen bonding. H, F, good, but they're not bonded together, so that doesn't count. And then, yes. Now, if I want them in order from lowest to highest in boiling point, once you have your intermolecular forces, it's pretty straightforward because the one with the most is going to have the highest boiling point, and the one with the least will be the one with the least IMFs. So it literally goes in order. So this one has the highest boiling, and this one would have the lowest. The second question talks about surface tension. So it says, put these in order from lowest to highest in surface tension. So what's the connection between surface tension and intermolecular forces? Good. So the higher the surface tension, the higher the IMF. So same thing. Yep, same order. So surface tension and boiling point are directly related. Now the last question talks about them dissolving. And it says it's giving you 2 substances. So it's giving you water and carbon tetrachloride. Let me draw that one over here. And we're supposed to pick which substance would better dissolve each of these molecules. So, what did we say? What allows something to dissolve in something else? Good, like forces. So let's look at these forces. So is water polar or nonpolar?
Polar.
This one is polar. And carbon tetrachloride? It's nonpolar. So things that are nonpolar will best dissolve in things that are also nonpolar. Things that are polar will best dissolve in things that are also polar. Like dissolves like.